All right, hello, and welcome to this version of the PyTorch Meetup. I will be the host of the first one. I will be talking about three very unique ways of applying machine learning. I'm Zach Akil. I am a machine learning engineer and a developer advocate at Google based in London. And looks like we've got a couple people here. Feel free to ask questions in the YouTube live chat, and then maybe we can answer them on the fly. But yeah, the goal is hopefully you're all maybe a bit familiar with machine learning. Maybe some of you are machine learning engineers, and my aim is to show you at least one thing that you've never seen before in machine learning, like one technology that maybe you've never thought of that could apply to machine learning. That's my goal. And the way I'm going to try to achieve that is by showing you three of what I think are the most unique demos that I've built, in the hopes that maybe something will spark your imagination to try some new creative technologies. I'm just gonna check that. Yeah, audio's coming through good. Okay, let's get started. So I've got three demos. Yeah, a bit of background on me. So I'm a big fan of anything hardware related. So one of the things that I've built is built this RGB neural network visualizer. So this is giving a real-time visualization of a neural network that's being trained in scikit-learn, and it's using the Raspberry Pi to turn on LEDs to represent the weights that are being found. And I just made it because it looked cool. And there's this other thing that's a good example of the kind of work I do, which is this robot that I built. I think it was like last year. And let me. So this is a robot I built to install on my desk in anticipation of New Year resolution diets. And the idea was, yeah, using a machine learning model to make the prediction, but then also using the Raspberry Pi and some like servo motors to apply the predictions. And this is the kind of thing I like doing. So I like, whether it's a simple model, I just like applying it in some unique way to, actually just apply machine learning. Anytime you get machine learning working into a real application, whether or not it's a useful application, I don't really mind, but as long as it's some application. So that's what we're going to be focusing on today. So I'm going to be showing off a couple of models. Some are simple models, some are more technical models, but they're all going to be applied in what I think are pretty unique and useful ways to know about. So that if you ever have an idea that you want to apply, if you remember back to the technologies that I might be showing, they might come in handy. So it's not so much I'm going to go into depths about the model specifics or the technology specifics, but I just want to show what technologies are out there for applying machine learning in different ways. So yeah, feel free to add anything in the chat if you've got any questions during these, but I'm going to be in the icebreaker that Karina is going to be hosting after this. So hopefully you've got a link to the icebreaker for after this. So I aim to spend maybe 30 minutes or 35 or 40 based on questions, and then we can ask questions in the icebreaker and stuff. So I've got three unique demos to show. First one's basketball related. So a while back, I wanted to try basketball because there was a basketball place near where I lived. And I went out there, I tried to shoot some hoops, and I was pretty bad at it. And I got pretty frustrated. But in that frustration, I started thinking of ways I could build something related to it. And the idea was that, okay, if I can't get it in the hoop often, maybe I can make something that looks cool. And so what I did is, actually in this previous image you can see better, I put some reflective tape on a basketball, so along the seams, like the reflective tape you get on like traffic cones. And then I recorded a video of me taking some shots, but had the flashlight on my camera enabled so that it would reflect back, so that I could see the ball more easily. And the idea was this: I wanted to create this kind of long exposure art, but I didn't have the fancy camera to actually do that with like opening up the lens. I just had my phone. I figured, oh, maybe if I just record the ball and have the ball shiny, it will look nice. It didn't. So this is what it looked like when I loaded it into Python and then tried to like catch every time the pixel was a certain color threshold. So it didn't look that cool. But then I started to kind of pivot the idea. Rather than making something that looked cool, maybe I can apply like some machine learning to it, because what else do you do really? So the idea was, this kind of looks like points on a graph. Like maybe I could plot a line or fit a line to it. And in anticipation of what I was going to do, I want to give a bit of background in case people aren't familiar. So yeah, you've got linear regression, fitting a line to some points. But a thing I want to bring your attention to is that if you fit a line, you can examine the actual sort of coefficients that got learned. And sorry, oh, my face is blocking this link. So if you want to see the animation, maybe I can bring myself down a bit. There we go. That's just a link to a tool you can use to like experiment with a linear regression thing. But I want to draw your attention to the fact that after we fit a linear regression, we can just examine the sort of coefficients it's learned and maybe extract some insight from the actual model itself rather than use it to make predictions. You can look at the model that got trained and develop some insight for the problem. So that's one thing I want to put in your minds now, because what I ended up doing was kind of exactly this. I wanted to fit a line to it, but a straight line wouldn't fit to my sort of shot data. But if I just create a machine learning model, and instead of it being a linear equation, it was the equation for a trajectory, then maybe I can fit the trajectory line to my data, which should fit because it was a trajectory curve that I threw. So that's exactly what I did here. So I created a model. In my case, I use TensorFlow, but you can use whatever machine learning framework you're comfortable with. But I created a trajectory curve from just the Wikipedia page. I pasted that over, and I set the sort of learnable parameters of the model to be the angle of the shot and the power of the shot. So those are the two main variables inside a trajectory curve. So those are the two things that I'm going to task my machine learning with optimizing to fit the line to my shot data. So here's the data from my shot that I made, and this is an animation of the line actually being fit using the TensorFlow to fit the equation. So I'm like, okay, that's kind of cool. So I can work out now, like I could use this as I normally would in machine learning, which is make predictions. And if I were to do that, what would I be predicting? Well, I would just be predicting the rest of the shot, I guess, which is not that interesting. Like I know where the ball is going to go. But what is super interesting is I can examine the sort of final state of the model that got learned and look at, say, the angle coefficient that it found and the power coefficient that it found. So by running this model after it's finished training, I now can look at the exact angle of my shot and the exact power of my shot. And I think that's a bit more interesting than just predicting where the ball is going to go next. So I was thinking, okay, how can I now productionize this? Like if I wanted to work out the exact angle of all my shots, well, one, how is that even useful? And as it turns out, in basketball, it's really important to be consistent if you want to be good. I guess all basketball players shoot at a very specific angle. Some of their angles may be different, but they all shoot consistently at the same angle. And so I figured, okay, that could be cool. It's like a training tool to work out how consistently you're shooting. So that was the idea. I want to productionize this now. This training tool that's going to tell you the exact angle of all of your shots. I'll check the comments and see if anyone's asked any questions so far. Okay, no questions yet. Okay, so how did I productionize this? Well, I used a technology, first one on the list, TensorFlow.js. This one I suspect quite a few people may already be aware of. It's a way of running machine learning in web browsers. And you can export PyTorch models into TensorFlow.js. I did do some research and I found out that is possible, so this is still super useful to know. And in my case, I was using Keras, so I was doing some post-processing on the video, and then I was exporting the models I was building into TensorFlow.js to run in the web browser. And this is all fine and dandy, but let me actually just show you the demo, because that's the good thing about it being in the web browser. And in fact, I've got a nice demo here. So on the GitHub page for it, I have the different apps, and I have the apps in different stages. So here's the first stage of the application, which is just predicting when I was making a shot. So if I run this, hopefully it's a bit small, but zoom in here. So this is video footage that's being fed in real time in the web browser to the TensorFlow.js models. And there's a model running that's tasked with just predicting when I'm making a shot. So just don't tell me anything about it. Just tell me when the ball is in the air, kind of thing. You can see here, when the ball's in the air, yep, it spikes. So that's good. That model's working. And the cool thing with this technology, because it's running in the web browser, I'm feeding in a video here for demo purposes. but it's relatively straightforward to then feed in the webcam, which is super cool for doing like sharing of the model. I can send anyone this link and they can immediately run the model with their webcam. I'm not in a basketball court right now, so it's probably not going to work. However, actually, maybe if I can simulate, I'm going to try to throw something and see if it works. Oh, yeah. It kind of spiked a bit, but it's not a basketball, so we all know how overfitting works. So this is the first stage, predicting when a shot's being made. The next stage, I'll just jump to the last stage. This is tying together everything. I had to have a couple of models to kind of crop out the shot data to then fit my my trajectory line to. And so I have a model that predicts when I make a shot, and then a model that predicts where I make the shot from. You can see that little, you might be able to see a flash of a red X. I don't know if the frame rate's going to be good enough, but there's one model that says, okay, when is he making a shot? And the next model says, okay, where is he making the shot from? And the reason I've got that model doing that is so that I can then crop out all the data points, and you can see all those data points here. So it's nice, clean. You don't see me in the image. It's just the trajectory shot. And then I'll enable this. And what this is then going to do is, after I've predicted where the shot is, and I've got the data points all nice and clean, run my fitting of the trajectory curve model on it, and here it is. So it's fit the trajectory curve, and I can just look at, see, okay, what angle did you find for my shot? In this case, that one was 57 degrees, the last one was 53 degrees. And so here's the first example of applying machine learning so that other people can use it. So in this instance, this is now a website that anybody can go to, and what's super neat is that this can also run on mobile devices. So if you just go to this website on a mobile phone, you'll be running machine learning on the device without having to install anything. And as I showed before, you can enable camera so that I could go to the basketball court, set up my phone, and begin using this application. So that's it. There's the first example. Let me stop playing this. First example. I'm going to have a slide at the end with all the links to all the tech I mentioned, but that's the first one out of the way. So TensorFlow.js, if you haven't already heard of it. The next one, biking. So I live in London, and I cycle to work. Well, I used to cycle to work, not anymore. And I would class cycling in London as an extreme sport. And most of the people I talk to and share this demo that I'm about to show also see that it is quite extreme, and an application like the one I'm about to show has a lot of use. So the idea was this. So I was cycling to London one day, or I was cycling to work one day, and I was being vigilant. I was looking forward, looking backwards, and then I wanted to turn right. Turns out I didn't look backwards at the exact right time, and I cut someone off. Like, they didn't fall over or anything, but they did verbalize their feedback towards me. And I was like, that sucks, because I try to look forward and backwards as often as I can to be aware of my surroundings, but some cases there's just so much going on you need to look both forward and backward at the same time. And you might be thinking, can't you use a mirror? So what I built here is I used some machine learning, and I wanted to do some real-time classification of what's behind me. So the idea was, with a camera on the bike, I could run an object classification model that would detect the different bits of traffic. And I wanted a kind of simplistic way of telling me that I didn't need to look down at. And so the idea was to have some like LEDs on the handlebars that would warn me when something dangerous or something I should be aware of is coming from behind. And the cool thing is, if I'm running object detection, I can make the LEDs different colors based off of the different amounts of danger that I think I'm in. So if it's another cyclist or a pedestrian, maybe it can just be green LEDs. But if it's like a truck, you want to be like flashing red. So that's where I think this could be a bit better than a mirror, because it can warn you very more intuitively than just trying to look at the mirror and trying to disambiguate what's happening down there. So how did I do this? So the idea was, first I needed to build a model, except I didn't build a model. There's an open data set called the Cocoa dataset. So if you're interested in experimenting or playing around with any kind of image classification, that is a great data set because it has examples of image segmentation, image object detection. But I didn't use dataset or train my own model. I actually just downloaded them all online because the Cocoa dataset has within its object detection labels, it has like the 5 different categories of traffic, like motorcycle, car, bicycle, pedestrian, and truck and bus. So I'm like, great, I don't need to label data, I can just use that. But I needed whatever thing I was going to use to run really fast. So that's where the next bit of technology that maybe not everyone knows about, and it's called an edge TPU. And it's made by a company, Coral AI. And they have 2 things. Actually, oh, I have it here. Great. Here is what I used. Maybe you can see it. So it's literally the size of a USB stick. And what this has on it is hardware that's specifically optimized for running quantized machine learning models. And so an example of quantized machine learning model is TensorFlow Lite models, but you can export other different types of models into this sort of quantized format to run super low latency. And what's extra cool, I mentioned that I didn't need to build a machine learning model. That is because on the Coral website, they have in their zoom in a bit here. They have in their tools and docs, they have a whole list of pre-trained models that are already optimized and quantized to run on this hardware. So for my application, I actually just needed to download the model and put it on the device I was going to use. So in my instance, I was using a Raspberry Pi to actually act as the brains of the app. And this just plugs into the Raspberry Pi to give it like a speed boost. And to show that off, here is, yeah, so here's this, and here's the setup I use. So the idea is you take your Raspberry Pi, and in this instance, I've got it plugged up with a camera module, and take your accelerator, and you just plug that into the Raspberry Pi, and there is a Python library and examples of how you can run Python code and tell the accelerator to make the predictions. And the speed difference I've seen is if I run a quantized model that's already been optimized for mobile devices on a Raspberry Pi by itself, it might make a prediction every 300 or 400 milliseconds, so maybe 1 or 2 predictions a second. But after I plug in the accelerator, I've got an example going here. After I plug in the accelerator, you can see the amount of milliseconds between predictions. It goes from 300, 400 down to 20 milliseconds. So that's 1 to 2 predictions a second to like 30 predictions a second. And that's running a full object detection model. You can see how like crazy cool it is, the fact that you can have super low latency, pretty like advanced machine learning models running on a Raspberry Pi. And you can tell by the fact that it's just using the USB connection to the Raspberry Pi that it's not using that much power as well. So it's a super efficient, super fast way of running machine learning models. If you need like a mobile application, like you need it to be, rather than it being in like a mobile phone, maybe you want it to be deployed in some IoT point in your house, like a weather station or camera trap, these sort of things. Anytime you need super low latency and the mobility, this hardware, Edge TPU, is really cool to look into. And I presented a talk all on this sort of invention where it's like a smart bike at PyData. And so if you search PyData Zack TPU bike, you can see the full 40-minute talk about sort of how the technology works and the process of building something like this. So yeah, that's 2 out of 3. And I suspect there's probably going to be maybe a small handful of people who already like aware of this technology, already aware of like accelerators and things like that, and already aware of TensorFlow.js, so that's fine. I'm now going to go on to the final demo, and I am willing to bet that no one has ever seen what I'm about to show. I'm going to say it's going to be eye-opening for everyone. All right. So here's the final demo. The eye-opening tool and the eye-opening application is this. So there's this incredibly amazing iris data set. Okay, I'm kidding about this being the cool thing. So I suspect quite a few people are already familiar with the iris data set. If you're not, it's kind of like the hello world of structured data. So if you want to make predictions on just like columns of numbers, It's like the go-to. In fact, it's bundled in with scikit-learn, which I'm sure quite a few people are already aware of. So that's nothing new. Okay, so let me get everyone up to speed with this, because it's not the data set specifically, but it's what I'm going to do with the data set. So let me zoom in. I've got a Jupyter notebook here. Apologies for the, I don't know if the dark theme I'm used to using is going to come up. Okay, that looks fine. Okay, so I've got here a Jupyter notebook. I'm loading in, say, the Iris data set. I'm gonna run this. If you're not familiar with what this tool is, this is called Colab, and it's like a free way of running Python notebooks. If you search like Google Colab, C-O-L-A-B, like free to use, and has a lot of Python packages pre-installed. But I'm going to use this to install the Iris dataset. I'm also going to import scikit-learn, which, if you're not familiar with, is like a really cool open source machine learning framework that covers kind of everything except for deep learning. So if you want to do like decision trees, which is what I'm about to show now, pretty good for that. So I'm going to import the Iris dataset. You can see here we've got 4 columns of data. Each one represents a flower. So an iris flower, there's 150 rows. And each of these columns represents a feature of the flower. So the petal length, petal width, petal sepal length, sepal width. So 4 features, 150 flowers, 3 different types of flowers. We have the setosa, the varus color, and the virginica flower. All right, you can see that I've worked with this quite a lot. So I'm gonna plot out some of the data. So here's like 2 of the features plotted on a graph, and the color represents the classification of the flower. So we have the 3 flowers. Structured data. We're gonna use the sklearn to make a decision tree. Okay, I'm not onto the cool bit yet. Don't worry. Although this is scikit-learn is a really cool library. I'm going to train a model. It's going to train a decision tree, which is going to effectively just generate some if statements that's going to help classify our data. I'll make some score of how well our model does. Apparently, we perfectly classify it. But also, what's cool here is I can render out the decision tree. I'm like, okay, that's cool. It looks pretty complicated. I need a simpler decision tree for what I'm about to show you. So I'm going to go up here and I'm going to set the max depth of this to, say, 2. So I want you to classify my data, and you're only allowed to ask it 2 questions. Okay, so this is what we get now. All right. We have a much simpler decision tree. So how it classifies our flowers then, first thing it does, it says, okay, what's the petal length? If it's less than 2.4, you are a setosa flower. Okay, if you're greater than 2.4, come over here. And what's your petal width? If you're less than 1.7, you are a varus color. If you're greater than, you are a virginica. It doesn't perfectly sort of disambiguate them, because there's a bit of I think there's a few virginica in this. There's 5 virginica in this bin, and there's 1 varus color in this bin. Okay, why am I doing this? Why am I showing you what's like a basic decision tree? Well, since quarantine, I've actually been exploring a new technology that I've always wanted to kind of look into. And this one is called Blender. Now, I suspect maybe a couple of people have heard of Blender. If not, what Blender is, it is a 3D modeling, animation, simulation tool. Completely open source, free to download. And I'm about to show you something really cool that I discovered that I could do with it. So what I'm going to do, I'm going to open Blender. It's going to be all live demo here. If you haven't heard of it, it's super cool. The UI is pretty intimidating though. I have to say, the first time I went to use Blender, I kind of opened it up and then closed it immediately and didn't touch it for a couple of years. It's definitely not one of those tools where you can just kind of like play around with it without any tutorials. You definitely need, if you want to get into Blender, there's loads of really great tutorials online for how to use it. And I actually did a course on Udemy like 2 weeks ago, and it's been incredible. So it teaches you everything. So here's Blender 3D modeling. What is so cool about this, and what has it got to do with decision tree? Well, Blender is actually got a really cool feature where it has a Python console built in. Let me make some extra windows, and I'm going to create. Look at this. I can create a Python console, and it's running Python. And I'm like, what's so cool about that? I mean, there's quite a few tools already that have Python integration. What's so cool about that? It's like, well, this tool does something which I've never seen done before in an application, and I think it's the greatest thing ever. It also has this window. Maybe it's probably, is that, it's a bit small there, but I can just tell you what this window is doing is anytime I do something like, let me delete this cube here. If I create a new cube, if I remember how to create a new cube, I'm gonna go add mesh cube. If I create a new cube, in this little window here, it's told me the exact Python command that I would need to run to do what I just did. Now, I suspect some people are going to clock on to what I was doing here. So I can make a cube, and it tells me the Python command to do that. And it also like gives you some other information like, okay, this is created at 000 location. So if I copy that and I paste it into this Python thing, let me delete that cube again. I'll delete that cube, and I'll run this Python command. Look, it created the cube. I programmatically did something that I just did in the UI, but all in Python. And it has built into it like a, you can write text files and run the text files. Anyway, I don't want to stall anymore. Let me show you what I did with the iris dataset. I'm going to open here, iris. So what I did with the iris dataset, because it's Python, I can install any Python library I want. I installed scikit-learn to it. It already comes pre-installed with like NumPy, which is pretty cool. But here's what I've been doing. So I took, in fact, you can see the Python script here on this bottom right, although it's not important to read the code because I don't think you can. It's a bit too low resolution. But what I did here is I wrote the code that would import the iris dataset, and it would iterate through each flower. And for each flower, it would create a little marble. And based on the features of the flower, like the petal width and the petal length, I actually, as I wait for it to load, I sort of embedded that into the marble itself. So for example, if the petal width is small, the marble's width was going to be small. So that was one way I sort of embedded one of the features. But that's just one feature, and I set that to the width of the marble. I also set one of the features to be the bounciness of the marble. And this is where it kind of ties back to the decision tree I made. I needed a very simple decision tree because I only have a couple of kind of physical parameters that I can work with. And I only really thought of like these two, of bounciness and width of the marble. And because we have the decision tree shown in the Colab notebook, I then know that, okay, with those two features, I should be able to classify these marbles. So what I did, I embedded those features into their marbles like physical state. And Blender not only does like the 3D modeling, but it also does physical simulations. So what I have to do is if I click play, it's going to then physically simulate these marbles. And I created this marble machine, and it's running a bit slow because it's I guess I'm doing a lot of physical stuff. I'm going to turn off the colors. You'll see here, I've got this first little bit of the marble machine, which only lets in a certain width of marble. So that's going to classify, I believe it's the Setosa flowers. And based on the color, I've also put those here. So you can see they get classified. Oh, it's a physical simulation as well. Why are those falling? That is, so they're not hitting that. I must have clicked something or, okay, well they should fall in there. This is the cool thing with physical simulations. They break just like in the real world. So the first one should be falling into that bin. You get the idea. The first one's fall into that bin because they've got a small width. So that's like the first fork in the decision tree. And then the next fork, which was the, I think it's like the petal width or petal length. I have that embedded as the bounciness of the ball. And so the more bouncy balls will fall into the next bin, and the less bouncy balls will fall into the bin before that. So I hope you can see how incredibly practical this is, in that you can take a decision tree and productionize it effectively using a 3D rendering tool such as Blender. I have no idea why it's not falling into the first one. I think the collider must not be working or something. But we'll let this run through on this sort of no color setting so that it runs through a bit quicker. And hopefully, as these are all the flowers, so 150 flowers physically simulated. We're gonna reach the last couple here, and you can kind of think of this as a neat way to potentially teach people about how machine learning works, because these are features. They could be features of data, but we've got them as features of marbles, and these kind of ways of separating the marbles are like these decisions in the decision tree. And when I was building this, okay, I can pause that now. When I was building this, I had to continuously keep adjusting how far away these bins were. And you can think of that as like the optimization part of the machine learning, because I was literally looking at the color of the marbles, seeing how many were misclassifying, and move this accordingly. You see that all our red ones, they should have went in there, but they went there, which is fine. You can see they're separated out. I think, yeah, one marble escaped. So yeah, in theory, I could build this. Oh, another marble escaped. In theory, you could build this and you would have a physical machine learning model deployed. And you can see I even went through the effort of making like a little label for it. But yeah, I haven't I'm still building this, so in the next couple of days I plan to get this all like fully rendered out, because in theory, if I use I can make it look super realistic, but it doesn't run real time. So then what I have to do is I have to enable that and then let it run for like an hour to physically make it look nice on every single frame, and then I can put together a nice video and put it on Twitter, which is what this is all about. But yeah, there's the final tool that I'll show you. So yeah, again, this is Blender, free, open source, loads of tutorials online, and it's got a really nifty Python interface for like programmatically generating stuff. This is sort of the end of all the demos. I've got here sort of a quick page on everything. So these are the tools that I mentioned, and there's links to the GitHub pages related to it. There's no GitHub page for this one because I'm still building it, but if you follow me on Twitter, you'll be the first to know whenever I actually make it as a nice, pretty video. And I'll put up the code and stuff of how you can generate it. But yeah, that's the whole talk. I don't know if we've got any questions in the... no questions? Okay, awesome. Perfect. So we've got... I believe Karina has provided the link to go on to the icebreaker, which I think you're going to be encouraged to go to now. But yeah, that was the full video. If anyone has any questions they want to ask now, I still have time to answer them. I'll wait like another couple of seconds, and then I'll end the stream. Wait more second, and then I'll leave this up on the screen for like a minute or two. Nope, no. Okay, perfect. Thank you all very much for attending this meeting, and feel free to follow me on Twitter and then follow up with Karina for the icebreaker link. But yeah, thank you very much and stay safe.